In the previous lecture, we covered parametric tests for portfolio returns, and these tests relied on strong distributional assumptions, for instance, that returns are normally distributed. And the validity of the conclusions depend critically on how well these assumptions hold in practice. And if these assumptions were violated, then the parametric tests can lead to misleading results. On the other hand, non-parametric tests provide an alternative approach and require much weaker assumptions about the underlying distributions. For instance, sometimes they can assume that the data is continuous or that the data is symmetric about the median value, but they do not assume the data comes from some form of parametric family like we did in the classical t-tests. And these methods become very helpful when, say, the sample size is very small or the data that we have are ordinal or ranked rather than the raw quantities, or when we require that our tests are as robust as possible. So when robustness of the test is a priority, then we look to non-parametric methods which do not require restrictive assumptions about the underlying distributions. And this is particularly useful with financial data because we have heavy tail distributions and a significant number of outliers. With what we know now, we can actually already motivate the construction of a hypothesis test. So this time, what we would like to do is to test the population median rather than the population means. So this time we will construct a null hypothesis that the median value is equals to some m0, and the alternative hypothesis, for example, could be that the median value is greater than this quantity. For example, you might want to test whether your portfolio returns has a median value of 0 or whether its median returns are greater than 0. So what is the median quantity? Now the median quantity is the value such that the probability of a random variable being lesser than equals to this value is equal to exactly half for a continuous distribution. So for example, if you have a normal distribution, we know that roughly half of the data points here sit on the left of this mean value because we know that the normal distribution is symmetric. And the other half sits on the right. Suppose we pick a data sample from this distribution. This is any distribution, right? So we pick a data sample from some unknown distribution, say f, then the probability that this value is lower than the median is exactly equals to half. By definition, the median value is right smack in the middle. So that if we were to pick out a random sample, it can either sit to the left of this median value or to the right of this median value. So in our hypothesis test, we only assume that the data comes from a continuous distribution. So this means that our cumulative density function has no jumps because we're working with a continuous function. Right? So for instance, here we could have 0 and 1, the cumulative density function. And we obtain this by integrating the probability density function from up to a. So for example, here we could have the point a. So how should we test for this set of competing hypotheses? Now suppose you have, again, n data points from some unknown distribution where the median value under the null hypothesis is this m0. We're going to define a test statistic S, which is equal to the sum of the indicator random variables of whether xi data point is greater than the median value. So this is essentially the number of data points greater than the median value. And we can look at these individual events, and what did we say before? By definition, the probability that one of these x of i's is greater than the median value is exactly equals to half by definition, and therefore each of these trials are Bernoulli random variables with probability half. And since S is a sum of n independent Bernoullis, S is a binomial distribution, parameterized by n and p equals to half. And that makes perfect sense. We know exactly the cumulative density function or the mass functions of a binomial distribution. In particular, we are going to observe some test statistic as observed, and the probability that the test statistic is greater than this observed value under the null distribution is going to be given by the sum from k equals to s observed and choose k and 0.5 to the power of n. And this is because we have 0.5 k and 1 minus 0.5 to the power of n minus k. And we know that these are equal, and this is exactly equals to the power of n. So this now is our p-value. So this is our p-value, and if this p-value is lesser than the alpha significance level, then we can reject our null hypothesis in favor of the null hypothesis that our median value is greater than this m0. So if we want to test whether our portfolio returns has a median returns greater than 0, then we are going to count the number of return data points that are greater than 0. And this count has a binomial distribution. And because we know what this distribution is, we can now compute the p-value, or we can compute the probability of observing this count, or more extreme than this count. And this gives us the p-value, and we can compare this to our significance level. This would instruct us to whether we want to reject or not reject the null hypothesis. Now we want to be very clear what we are testing for. Here, we are not testing for the mean of the distribution, we're testing for the population median. Again, we can go back to the previous example where we had this portfolio return from selling deep out of the money puts. And what we observed was that this is a very negatively skewed strategy. And this kind of a return distribution is very likely to have median returns greater than 0, even if the mean returns is equal to 0 or lesser than 0. So even if the expected value of this strategy is negative, if you are skewing our portfolio returns enough, then the test for the median would still show up as positive. And we have in fact seen this in our previous lectures on the algorithmic cryptocurrency trading, where we performed regressions for the returns of a trend following strategy. And we saw that the trend following strategy has a positively skewed returns. And when we perform the regression, we actually get a different scope depending on how we aggregate data. So for those of you who did not participate in the previous lectures, I'm going to leave you a link where I explained how regression analysis can give us information about the skew in your return distribution. So this only makes use of the sign of the data points. However, if the data happens to be symmetric around the median, so for example, if the median value is here and the density function is symmetric about this, so suppose our distribution, the underlying distribution is like this or like this, as long as it is symmetric around the median, we can actually do better because the sign test only takes into account whether our data points are to the right or to the left of the median. But we can also take into account the magnitude of the distance or the signed ranks. And it turns out that we can construct what is called a Wilcoxon signed rank test for the population median. It relies on the assumption that the distribution is symmetric at the median value. And under these assumptions, we can construct a more powerful test by taking into account the magnitudes of these signed ranks. We're not going to go into the details of this hypothesis test, but of course you can read it in the lecture notes, and we're going to implement this inside of the Python lectures. So the sign rank test improves on the sign test by incorporating the sign of the differences as well as the magnitude. Now, assuming symmetry, the Wilcoxon sign rank test is a more powerful test than the sign test, and both tests do not assume an underlying distribution. The Wilcoxon sign rank test does assume that the distribution is symmetric, and both that the underlying distribution is continuous. So finally, we have introduced both parametric and non-parametric tests for location. By location, I mean where is the middle of the distribution, and we can determine this by the mean or the median. And we have introduced the hypothesis test, each of them requiring a different set of assumptions. We would like to move on and implement this inside of Python. Now, of course, we would like to move on from the returns framework to a more flexible and powerful machinery involving resampling and permutation. So, finally, we can move on to this chapter and talk about how we can use a different method to simulate or to generate the null distribution. When it comes to the Monte Carlo framework, the hypothesis test also assumed the similar structure, but we differ in how we simulate the null distribution.